Okay, so finally we have this boundary value problem. I know I don't have that much time here, so I'll kind of go fast here. So here's the semi-linear problem that I want to study. It couples to this linear problem, so it's really this coupled system I have to solve. And then there are potentially boundary conditions of mixed type on different parts of the domain. You know, the typical setup that I'm interested in, if I actually want to do computing, is that I have, say, a sphere or some other finite domain that has maybe some embedded black holes or neutron star interior structures, in which case I would have then boundary conditions on an interior surface. So it would be a non-simply connected kind of three-dimensional domain. And the domain M is either an open set in R3 minus some holes, or possibly, depending on what the application is, possibly a three-manifold that has non-trivial topology. And then this is just some shorthand for the coefficients that appear here. The key play is AW is the term that depends on W. B tau is sorry, this term here, because phi appears explicitly, is a term that depends on phi. What else do I want to say here? Again, what we do is we think about this as just some big coupled nonlinear system. We do Newton's method using linearization. And it turns out that the PDE problem here, even though this has been studied since 1916, and in particular this constraint system has been studied more or less since 1950s, and this particular form that I've written here has been studied since 1973. It turns out there are quite a few open questions still just about the PDE problem here, and in particular, what I needed were L-infinity estimates. So I need to have the continuous solution bounded in L-infinity, and I need the discrete solution that I'm going to produce using finite elements bounded in L-infinity a priori, in order to have both the linear approximation and the nonlinear approximation frameworks to do these adaptive algorithms. So these were not available other than in very special situations where the two equations decouple. And then, of course, there are other situations that were of interest here that I'm not going to talk about. One is, if this is a three-manifold, then what I'm typically going to have is a triangulation of it. So I'm not actually going to have, and what I'm going to build then are finite element spaces on a triangulation, and I'm not going to actually have a subspace. In fact, what I'm going to have is some other approximation space, an exterior space, and I have to account for the fact this is not an approximation, this is not a subspace. So you can look at, there are some papers by Gerd Zook on this with Alan Demlow, and some earlier things by Gerd Zook actually in the 80s for the Laplace-Beltrami operator. And also some more recent things by Riccardo Nochetto and a recent PhD student. And then we have some sort of more general versions of this for the semi-linear problems that I'm not going to talk about any further here. But basically we have a way of dealing with how you develop approximation theory in the case that you don't build subspaces. And then we have these other questions. Linear approximation, nonlinear approximation, we need these L-infinity estimates. And then we have the question of convergence and optimality of these algorithms. So the first thing, these a priori L-infinity estimates turn out to be one of the key things to developing a solution theory, and in particular to answering this open question that was sitting there once we started to look at this. And then there was another question about, can you actually solve this constraint system if the background metric that's sitting on your three-manifold that's giving you the differential structure is only in some weak Sobolev class rather than being, say, a C-infinity metric? And it turns out there's a lot of interest in this question, in addition to this existence question. There's a lot of interest in this question because of a lot of recent work done on the evolution equations. People are interested in how rough the background data can be in order to support what's referred to as rough solution theory for the evolution equation. So there's sort of a technical reason to look at this question. Okay, and so when this term is zero, the two equations decouple. When it's not zero, they couple. But if you make this term small, referred to as the near CMC condition, which I've written down here in a very more precise way, then you can develop a fixed point argument for the coupled system. When there's no restriction on the size of gradient tau, there was no theory. So what we did was develop a different kind of fixed point argument based on direct line compactness arguments, and then based on a priori L-infinity bounds, more or less. It's based on really the construction of what's called barriers, which are sub and super solutions, but it gives you sort of after the fact a priori L-infinity bounds, which are what we needed for the approximation theory. And so we have some recent papers on this sort of barrier construction, which is key to developing the solution theory that gets rid of this near CMC construction. And I'll just point at the papers at the end. There's a little explanation of these barrier constructions. And then I just have a couple numerical examples from a recent paper using FEDK to do the Hamiltonian constraint, just one of the two equations. This is for the near CMC case, or for the CMC case where the two equations decouple. This particular type of meshing was done to allow FEDK to be used as part of an evolution simulation. There's a large group in the numerical relativity community that has developed a piece of software called Cactus that is it's a very general piece of software. It's in some sense similar to the FEniCS project, but it was designed by people doing numerical relativity, and it's essentially a finite difference code, and it's really focused on evolution problems of sort of large coupled hyperbolic systems with possibly side constraints. But it's very flexible. It's a sort of a modern, C++ software engineering effort. But they don't have a good way to do sort of non-trivial topologies, and in particular for producing initial data for the constraints. So the effort here, the joint project, was to use FEDK to develop initial data, solve the constraints on some non-trivial domain in the presence of some non-trivial matter densities. And so they have what's called a multi-block discretization, which allows them to use are essentially uniform meshes in cubes, deformed cubes. And so the challenge was to sort of build our tetrahedralizations into these domains, and then to allow us to also do additional adaptivity from this base tetrahedralization. And so these are just some pictures from that software, from that effort that I'll point to the paper in a second here. And you can produce, so it produces initial data for black hole domains or for neutron star type domains. Just a couple words about my collaborators here in the papers. So the fast solver work actually is here. Again, I didn't talk about this at all, but this just outlines what we do in FEDK to get linear complexity solves in these Newton type iterations for adaptive settings. The parallel stuff, that the way we actually do decoupling so we can do adaptivity on parallel computers in a reasonably efficient way, is a long paper with Randy Bank here. The problem I didn't talk about, this first example, that's another semi-linear problem that's outlined in my slides. This is the paper I mentioned that kind of explains this setup in a very, explains this problem and how it fits into this framework in a very clear way. One of the key things here, again, was to establish a priori L-infinity estimates, both continuous and discrete, which is a big fraction of the paper. And then there's a sort of a more primitive convergence theory argument for an adaptive algorithm. And what we have is sort of an improved version of that, but that's the first version was in this paper. This is a little bit of the parallel work that I did with Don Eastep and Mats Larson, who I think a lot of you know. This is sort of an analysis of the algorithms that Randy and I looked at. This is the new solution theory. These are just sort of papers on the PDE problem that I just talked about. This is actually another paper on the parallel stuff. What I just showed you as far as the convergence theory for the constraints, the a priori L-infinity estimates, which I didn't drive for you, but they're sort of the key to doing the linear and nonlinear approximation theory for the constraints, are in these two papers. And then this is a new effort. I didn't actually talk about this today. The convergence theory I talked about today is basically in these two papers. But we have a more general version of this now that works for a more general class of nonlinear problems that I'm going to talk about next week in Munich. And I have a preprint of this if anyone's interested. I'll just leave it at that. The pictures were from this manuscript, which was just accepted. This is actually using FEDK to solve the Einstein constraints as part of an evolution. The mesh generator stuff is all these are PDF files on my webpage or links to the journal articles. The mesh generator stuff is described in these two articles here, and I guess that's it. So I'll stop.